Simple but high-accuracy approximation for n factorial by Stephen Pigeon, professor at Université du Québec à Rimouski. The factorial arises in a number of computations, ranging from combinatorics to theoretical physics. The usual series proposed to compute n factorial, other than with integer-only arguments, is Stirling series, or Stirling approximation, or Stirling function, depending on who you are reading. It is shown here in equation 1. But this infinite series cannot be evaluated in full and therefore must be truncated. One might want to truncate it only to its first two terms, as shown here in equation 2, as a good trade-off between accuracy and speed of computation. However, truncating its series to only two terms greatly reduces precision. To compensate, Hodgman, in its 10th edition of the CRC Standard Mathematical Tables of 1955, proposes a correction, a -1 in the denominator of the second term, shown here in equation 3. This approximation, that I've seen nowhere else, quite intrigued me, so I put it to the test. Simply truncating the series underestimates the factorial. Hodgman correction overestimates it. But since the general form, here shown with plus or minus alpha, is a continuous function by the intermediate value theorem, or more precisely one of its special cases, Bolzano's theorem, there must exist a value for alpha for which the error is 0, that is, for which it ceases to be an approximation. So, let's find it. Alpha could take any form, but since we're interested in simple approximation, we will limit ourselves, quite arbitrarily, to rational functions of low degree d in n. Let alpha dn be that rational function, and p alpha d the approximation using it. Let us remember it as equation 4, as we will return to it quite often. To find the optimal alpha, we notice that the square error is convex in alpha, so it suffices to solve its derivative relative to alpha equals 0 for alpha. Using Stirling series for n factorial, we find that solving the derivative of the error relative to alpha is equivalent to solving equation 5 for alpha. We reorganize equation 5 to get equation 6, which is a much more convenient form to work with. It will allow us to find alpha for any desired degree d in n. Let's start with a constant alpha. To find an optimal constant alpha, we use equation 6 and keep only degree 0 terms, that is, constant. We find right away that the optimal alpha is -1/2. We put it back in equation 4 to get equation 7. While it's tempting to see that result as some kind of average between truncated series, correction of 0, and augmented correction, -1, but no, it's actually an explicit minimization of the error. It is the optimal solution. We can use this strategy for any degree. Say now 2. From equation 6, we keep only the terms of degree 2 or less, and we find that alpha is -1/2 plus 7032 n plus 293 over 17,280 n squared plus 720 n minus 556. We place this result back in equation 4 to get equation 9. Note that the equation numbers match the full paper that will appear in IJAPM. Note also that equation 9a and 9b are strictly equivalent. They're just different forms of the same equation. We will now compare results. First, let's consider the error function. Here, we will use the absolute relative error. Let us now compare constant corrections. Here we have Stirling's series, truncated to its first two terms. We have Hodgman's correction, and our solution with alpha equal -1/2. We see that our proposed solution does really better than either two alternatives. We also notice strange noise in the lower right part of the graph. This is actually where our solution reaches machine precision. Basically, float and rounding errors are bigger than the error from the approximation. In the remaining results, we'll use arbitrary precision to avoid those effects. Now let's have a look at better approximations. Equations 7 to 10 correspond to our solutions, from degree 0 to degree 3. Equation 11 serves as a baseline. It is Stirling series without the correcting terms. To compare, we also have included other approximations. Those are often cited in literature. Those are Burnside's, Gosper's, and Martichi's. Here we have a log-log plot that shows error for the different approximations. As expected, the error goes down as the degree goes up. We also see that the error goes down as n grows. It means that in a way, the approximation gets better as n grows. We also notice the two strange dips in equation 8 and 10. This is where the approximation crosses the real function, where the approximation is actually equal to n factorial. Again, we have here a log-log plot. From the graph, we see that Martichi's approximation does unnoticeably better than Stirling without its correction terms. We also see that Burnside's approximation does just a little bit better. From those three, it's Gosper's approximation that does the best. But even then, we see that it does worse than our proposed solutions. Let's now have a look at two good approximations. The first one is Mohanty's and Roman's, and the second one is AMMS. Let's observe that the exponents depends on n. Here again we have a log-log plot. From this plot, we see that Mohanty's and Roman's approximation is quite comparable to our correction of alpha equal minus 1/2. What we cannot see from the graph is that it does just a bit better. AMMS correction does better than equation 9. Just a few percent better, but still better. Let us remember that equation 9 uses an alpha with a degree of 2. In all cases, equation 10, an alpha of degree 3, does really better than any of the other solutions. Here are the same results now presented as a table. From the table, it is now clear that equation 9 and equation 16, AMMS approximation, are about the same, with a slight advantage to AMMS. From the table, we also see that equation 10 does much better than all the other approximations. The correct number of leading digits is also interesting, as it is related to the attainable precision on float with limited number of digits. Here again, we see that equation 9 and equation 16, AMMS approximation, are roughly equivalent. They have the same number of correct leading digits. However, equation 10 does much better than either, as it adds at least 3 other correct leading digits. Now a word on complexity. Most of the other approximations raise the correction term to the nth with the nth plus or minus 1/2 power. This requires at least order of log n steps. Our proposed solutions are, at least for the correction term, evaluated in order of d, the degree, regardless of n. Moreover, we may be able to find some efficient way to evaluate the rational function. In our example, we reduce the number of product from 10 to 6 and cut one division, just by reorganizing the formula and factoring out n squared. In conclusion, we have a new class of approximations for n factorial. We have shown that they can have very good precision. We've also shown that we have an adjustable trade-off between complexity and precision. And finally, we have shown that it may be amenable to efficient implementations. What we haven't discussed but may be worth exploring is how much better rational functions play with precision compared to, say, approximations that use trigonometric function, infinite series, or continued fractions.